Hello everyone, thank you for joining this on-demand webinar. I am Benjamin Hall, Application Engineer Team Leader at Basler Asia. Today, topics will be on choosing the right lens for your machine vision camera. Basler positions ourselves as a vision solution provider, and we recognize that optics can often pose a challenge for many vision system engineers. As you can see, lens performance in machine vision system can be influenced by various factors. When it comes to choosing the right lens for your machine vision application, you find yourself navigating a complex landscape of various optical parameters and considerations. The sheer number of factors to be considered can be quite daunting. So let's crack the nut by focusing on the most important thing you need to consider when selecting a proper lens for your machine vision application. Let's take a look at agenda for today's webinar. First, we introduce you the key step to find the right lens for your machine vision cameras. Second, a little history to start with. This topic, we will tell you about the history of lens design. Third, how to tell lens performance. This will help you to analyze the performance of the lens. Fourth, how to balance cost and performance when choosing lens. And the final topic is the key takeaway for today's webinar. Let's start our journey with a small task. Now you have a Boost V camera in hand, and you would like to get a proper lens for it. How will you proceed? I have listed all the key specifications of the camera for you, which show on the slide here, like pixel size, sensor size, resolution, and etc. Here are the key steps for lens selection. Basic lens selection can be done by following 4 steps manually. First, find out the image circle you need. The rule of thumb is the image circle must be bigger or equal to the sensor size. Second, calculate the focal length based on the formula below. Focal length equal to working distance divided by magnification plus 1. Then calculate the right lens resolution and pixel size. Pixel size in micrometer equal to 1000 divided by 2 times pixel size in micrometer, which equal to 500 LP per mm. And the final step is checking the lens mount for cameras. With these 4 parameters, you can visit Basler website to select a suitable lens. Of course, you also can use our online lens selection tool on the Basler website. But what if when you can't find a suitable lens, example like no ideal focal length match, more than one recommendation, or even no recommendation? As we know that the basic step previously introduced only help you to select a lens for your magnification, working distance, and other mechanical requirements. For many cases, the critical factor is whether you can see the target object clearly or not, which related to the lens resolution. Lens resolution refers to the ability of the lens to resolve the fine detail in an image. So through the webinar today, we aim to enable you to understand the logic behind optical decision in machine vision application. Before we talk detail about lens performance, let's start with the history of the lens design. Between 1846 and 1866, Carl Zeiss workshop manufactured consistent high-quality microscope according to a very strict rule of craftsmanship. Due to that time don't have any formula or design methods, lens maker only can use trial and error way. But Carl Zeiss refused to accept the trial and error way method used at that time to produce optic lens. He knew he needs a scientist. In late 1866, Annie Abbey joined Carl Zeiss, and for the next 6 years, they teamed out intentionally to lay the scientific foundation. Abbe is remembered to today for the formula he concluded to calculate the possible resolution of the microscope. To avoid the previous trial and error method, Snell's law or the law of diffraction was used to calculate the lens. Snell's law is a formula used to describe the relationship between the angle of incidence and refraction when referred to the light passed through the boundary between two different isotropic media such as water, glass, or air. Snell's law equation is n1 sine beta 1 equal to n2 sine beta 2. Beta 1 is the angle of incidence. Beta 2 is the angle of refraction. But Snell's law introduced trigonometric function. This is very tricky to calculate sine beta. So sine beta was replaced by beta for a simple calculation. Beta is the angle between the light beam and normal vector of the surface. Beta equal to sine beta can be true when the beta is very small, which almost equal to 0. In that case, only the light beam nearby the optical axis can meet this assumption. Refer from the previous page, you can see how the angle beta is increased outside the lens. These increased beta are reasons of error which do not following the calculation and called as lens aberration. Lens aberration refers to the imperfection or deviation from the ideal optic behavior of a lens. This imperfection can cause various types of distortion or error in the image formed by the lens. To reduce the lens aberration, we should use the light beam only nearby the optical axis. How can we do that? The easiest way is to reduce the lens aperture size. By reducing the lens aperture, all the light beams at the edge of the edge sides are blocked by iris, and only the light beam on the center can enter the lens. So the smaller we close the lens aperture, less the aberration we have, but diffraction effect is increasing. What is diffraction? In next topic, we'll go to tell you more. Before we introduce diffraction, is the following statement correct or wrong? Lens working better near the optical axis, so we can reduce the aperture for the better image quality. The answer is wrong. Why? In context of optics, diffraction is particularly relevant to behavior of the light wave as they pass through a small opening or a round obstacle. When the light encounters a small aperture like the opening in the camera lens, it undergoes diffraction. The illustration shows that the diffraction effect is low at the large aperture and high diffraction at a small aperture. As you know, the aperture of the lens does not simply control the amount of light. Adjusting the aperture also affects the lens aberration and diffraction. Let's see the relationship between aberration and aperture. As shown in the diagram, when the lens aperture is open, the aberration increases. Aberration occurs because the ray of the light passed through the lens fails to converge a single point, causing the image formed by the lens to be blurred or distorted. For the lens with a small aberration, when aperture is small, the light beam is focused on a single point. Lens diffraction is sometimes unavoidable, but we can minimize it by opening aperture. When the diffraction is high, is affect the sharpness of the image. If you can remember the previous page about the aberration, aberration is high at open aperture and low at closed aperture. Therefore, aberration and diffraction represent opposite effect in optics, which aberration causing the dispersion of the light and diffraction cause the light wave to be spread or bent. However, lens aberration are not natural occurs but rather error introduced by human. Therefore, lens aberration can be improved through efforts such as careful design and high quality manufacturing. For this reason, even lens with the same aperture size can exhibit different level of aberration. Lens with high aberration, the ray focus at different distance. Therefore, high performance lens may minimize or no aberration even when the aperture is wide open, allowing them to be affected primarily by diffraction and result in better image quality. Diffraction and aberration can be observed on the modulation transfer function graph. On the left of the y-axis of the graph refers center of the sensor, and the y-axis on the right is the edge size of sensor. Higher MTF percent means better performance. As shown in the graph, center side on the sensor is mostly affected by diffraction. So MTF on the center usually high at the fully open aperture. While the edge size of the sensor is mostly affected by aberration, so MTF on the edge is usually high at close aperture. Here are some pictures that show you central sides of the sensor mostly affected by diffraction, so the image on the sensor is usually better sharpness at fully open aperture. While edge side on the sensor is mostly affected by aberration, so the image on edge is usually clearer at the close aperture. We will tell you what is the key factor affected by the lens performance. Lens brightness and lens resolution is the two important factors that influence lens performance in optical system. Let's go into more detail. Now we talk about numerical aperture and show you how it affects the performance of the lens. Numerical aperture refers to the cones of light that is made from the focusing lens, and it describes the light gathering capability of the lens. NA is defined by the following equation, where N is the index of refraction of the media, often N equal to 1 for A, and alpha is the half angle of the cone of light exiting the lens pupils. It is important to remember that F number and NA are inverse related. NA is equal to 1 over 2 times F number. F number refers to the ratio of lens focal length to its aperture diameter and indicate the amount of light going through the lens. So how the resolution of the lens related to NA? Rayleigh criteria state when two-point source of light on the object side pass through the lens and image on sensor, they no longer appear as two distinct point sources, but instead transform into concentric circle of specific size. These concentric circles are known as Airy dish. If the size of Airy dish becomes larger, the two separate point sources will not longer be perceived as two separate source points on sensor, and it will instead appear as a single point source. Reducing the size of Airy dish allows the lens to maintain smaller distance between two point sources that the lens can be resolved. NA is not only the an indicator of the brightness of the lens, but it also indicator of the resolving power of the lens. Therefore, using NA, you can calculate the resolution limit of a specific lens. As you can see from the formula, when NA increase, the diameter of the area dish D decrease, allow you to see smaller object. Therefore, generally, a higher NA result in a better resolution for the lens. Lens resolution determines how well the lens resolving image detail. NA and NA prime. NA related to the lens resolution, how small the defect size can be detected. NA prime related to the lens sharpness, how clear can see the capture image with the high brightness and contrast. Then, how can we increase the NA to improve the lens resolution? The simple way is to increase the lens magnification. The second diagram illustrates the change in the lens position when the magnification is increased. To increase magnification, the lens needs to get closer to the object, which results in a longer distance between the lens and the sensor. When the magnification is high, you can see object more closely and more detail. In this situation, the lens can see smaller object, but at the same time, the sharpness and the brightness of the object decrease. Conversely, when the magnification is low, as shown in the third diagram, the opposite occurs. The distance between the object and the lens is longer, causing the NA to decrease. But the distance between the lens and the sensor is closer, result in increase of NA prime, which allow for the sharper and brighter image, even though smaller object may not be visible due to the low magnification. Here the example. To see a smaller detail, we need to have a higher magnification as pictured on the right, but the image is very blurred and dim. NA and NA prime can be calculated using a following two formula. And I calculate the result of NA and NA prime of f number 2 lens separately increasing the magnification. We currently using an inspection device that have 1 times lens to detect a defect of 20 micrometer. However, the following equipment now need to be upgraded to a system that can detect 5 micrometer size defect. In this case, since the size of the defect has been reduced by quarter from 20 micrometer to 5 micrometer, most people think that if they can change the magnification of the lens to 4 times, it will be able to detect the 5 micrometer size defect. Is that really work that way? According to the calculation table, NA and NA prime are 0.125 for 1 times. And the resolution of the lens is direct proportional to NA. So if you want to see an object that has 4 times smaller, you need 4 times larger NA. So, but you look at the NA at 4 times magnification is only 0.2 NA. So what happens if you keep increasing the magnification? If you look at the table, even if it is 256 times magnification, it's only twice resolution of the increase as big as NA when it is 1 time. But the NA prime reduced by 0.008 times. As a result, even if you increase the magnification, the benefit of NA are not significant, but rather only very dark and cloudy images are obtained. How can we increase the lens resolution? The table in the middle shows the size of the finest detail can be resolved is proportional to lambda 2 NA. where lambda is the wavelength of the light. The resolution increases when the Na increases. But the best way to increase resolution is not simply to increase magnification and sacrifice Na prime. Rather, to increase the lens aperture to simultaneously enhance both Na and Na prime. Expanding the aperture can involve increasing the physical size of the lens or widen the entrance pupils by opening the aperture. However, as explained earlier, open the aperture will introduce aberration. Therefore, the key to the high-resolution lens is eliminating aberration to maintain the excellent resolution even when the aperture is open. This example shows you the relationship between lens resolution and camera pixel. Is the lens with the high resolution always superior to the lens with lower resolution when compared? You might find this illustration helpful for clearer understanding. When the camera's sensor only 18 pixels, you can see the image is blurred even with a high resolving power lens. In this case, a camera with lower resolution and larger pixel size, there may be no noticeable difference in actual image between the lens with excellent resolving power and the one with limiting resolving power. In such case, there may no need to use an overly expensive high-resolution lens for low pixel resolution camera. As a pixel increase, you may see the sharper image from the high-resolution lens. High-resolution lenses are typically more beneficial when the camera pixel resolution is high. So, how can we determine the lens resolution that corresponding to specific pixel size? The answer is lens MTF graph. MTF graph is the main factor to evaluate lens performance. Consider both contrast and sharpness. As introduced earlier, when point source of the light pass through the lens, they transform into the pattern known as iridescence. This transformation causes the lens not precisely transmit the object image to the sensor. Consequently, as shown in the illustration, a stripe pattern with alternate black and white bar is formed, and as the lens processes it, the pattern changes into sine wave light profile with black and white bar oscillating repeatedly, and the 100% contrast decreases too in the image size. The lens MTF describes how well the lens can reproduce different spatial frequency in the image. It quantifies the lens ability to transmit contrast at a various spatial frequency. If the lens curve shows that it can reproduce certain spatial frequency with high contrast, then the smaller pixel can capture this frequency more accurately because they have the resolution to do so. In other words, when the LED size within a pixel size, it corresponds to high MTF. Smaller pixel size can take advantage of the lens ability to resolve fine detail. Meanwhile, if the lens MTF shows poor contrast transform and certain spatial frequency, then no matter how small the pixels are, they won't able to capture those details accurately because the lens itself limiting the contrast at those frequencies. This is why it is essential to have an appropriate match between the lens MTF and pixel size. The MTF graph is continuous measure of the contrast reducing by narrowing the spacing of black and white stripe pattern. As the stripe spacing decreases, the contrast of the image passed through the image lens is decreased. Therefore, you can obtain the graph like the one on the right. X-axis of the graph represents LP per mm, which stands for line pair per millimeter. One line pair per millimeter means that one pair of black and white stripe within 1 mm, indicating the stripe spacing of 0.5 mm. Similarly, 10 LP per mm means that 10 pair of black and white stripe within 1 mm, and each stripe have a spacing of 0.05 mm. Using the same method, 100 LP per mm correspond to the stripe spacing of 0.005 mm, which is 5 micrometer. Therefore, the x-axis value increase, the stripe spacing become denser. The y-axis represents the contrast, and all the lens have the graph shape where contrast decrease as the stripe spacing become denser. However, lens with high resolution exhibit a smaller decrease in contrast. The MTF graph is typically divided into two main types: spatial frequency oriented and image height oriented. Spatial frequency oriented MTF graph, x-axis represents the spatial frequency in cycle per millimeter. Y-axis represents modulation transfer, typically ranging from 0 to 1. This graph shows the system ability to reproduce different spatial frequency. High value of the Y value indicate the system accurately reproduce fine detail. Conversely, low value indicate loss of detail. This graph is particularly useful in analyze the system performance in terms of resolving fine detail. It helps in understand how well the system can reproduce patterns of different sizes. Image height oriented MTF graph. X-axis represents the image height in field of view, usually from the center to the edge of the image. Y-axis represents modulation transfer, typically ranging from 0 to 1. This graph shows the system ability to reproduce detail as function of its position in field of view. It helps understanding the system perform across the entire image, from the center to the edge. This graph is important for assess how image quality varies across the entire field of view. It helps identify any optical aberration or distortion that might be present. Choosing between these representing depends on specific requirement of the machine vision system and what aspects of performance are mostly crucial for given specific application. For example, in the application where uniform image quality across the entire field of view is crucial, image height oriented MTF might be more relevant. In other hand, in the application where the resolution is fine detail is critical, spatial frequency oriented MTF might be more important. As previously explained, MTF graph is an indicator of how well the lens reproduces objects on the sensor. Therefore, you can use the MTF graph to determine how well the lens can accommodate the pixel size that make up by sensors. Based on Nyquist sampling theorem, if the pixel size of 5 micrometer, you can use this formula to determine the lens MTF at 100 LP per mm. Furthermore, this calculation result is based on 30% contrast criteria on the MTF graph. In practical terms, this means that to accommodate a 5 micropixel size, you would need a lens that have more than 30% contrast at 100 LP per mm in the MTF graph. In practical, lens manufacturers have decided to apply a more relaxed criteria when it comes to aligning lens performance with pixel size. This relaxed criteria involve multiplying calculation result from the previous page by a factor of 0.67. In theory, Not all the concentric circle of the array dish affected by lens resolution. Only the first concentric circle significant impact it. The first concentric circle occupied about 84% of the entire array dish. And the lens manufacturer have decided to accommodate a specific pixel size is sufficient if 80% of the first concentric circle within a pixel. Therefore, since only 80% of the first concentric circle, which make up 84% of the whole array dish, need to fit within a pixel, the factor of 0.67 is applied to the final calculation of this criteria. So the typical lens selection process is using 30% contrast at 0.67 Nyquist frequency. The total system MTF is the product of MTF of the lens, filter, image sensor, and electronic. When we look at the following two MTF graphs, you can now determine which lens have a better performance and can accommodate a smaller pixel size. From the MTF graph, it's clearly the one on the right have high performance. However, does that mean this lens on the right is always better lens? The answer is no. It always depends on situation. When the resolution is crucial, using the lens of the right may be preferable. But when the factor like brightness or cost effectiveness is more important than resolution, the lens on the left may be more suitable. Besides that, if the pixel size is large enough, you may not need the lens with the higher MTF on the right. Therefore, lens resolution does not determine everything. Choosing the right lens based on situation is more crucial. And for this, the ability or check MTF graph is essential. We will provide another example in next slide. Now, let's take a look of MTF of the Basler f-mount lens. This lens maintains of 30% contrast at resolution 150 LP per mm. In this case, how small of the pixel size can it accommodate? According to the calculation formula explained earlier, pixel size equal to 1 over 150 divided by 2, then multiplied by 0.67. In this case, it can accommodate a pixel size as small as 2.33 micrometer. Therefore, this lens is perfectly compatible with the pixel size of Basler newly developed Boost V camera, which have a 3.2 micrometer, which showed in the beginning of the webinar. Basler offers solutions that enable camera and lens to be used optimally together. Next topic is how do we balance the cost and performance when selecting the lens for machine vision camera. For industrial user, finding the right lens does not equal to finding the best technical fit, but rather finding the right balance between the cost and performance. So, how to select the lens which is sufficient for your application? Here, we can share is, there is no universal rule or simple function to help you to find the best cost-performance lens. It always depends on your application requirement. Meanwhile, you as our customers, you can always reply on Basler Vision expertise for consultation. Next, let's learn together through some use case how application influence the lens selection in terms of balance between cost and performance. First use case, a customer will inspect a fluorescent image from blood sample. When the fluorescent light is weak and the diffraction is small up to 1 mm, which lens will be proper to use? The pixel size of the camera is 5.86 micrometer. Because the application is not sensitive on resolution, but the brightness, we decide the resolution we need to mesh as 2 × 2 pixels equal to 11.72 micrometer. So 1/2 × 11.72 micrometer times 0.67 equal to 28.58 LP per mm. Look at the two MPF graph from these two different lens. The lens on the left with the smaller f number or called as a fast lens will be more suitable for the customer in this use case. Next case, the customer want to detect a defect on the wafer surface. The minimum defect size is 110 micrometer. The wafer diameter is 100 mm. This use case resolution is essential. To see the detail of 110 micrometer, we need 4 × 4 pixels for one detail, which equal to 27.5 micrometer. And with the FOV equal to 100 mm, the camera resolution at least needs 50 megapixel. Basler boost camera is selected with the following specification. The best technical fit is priority for lens selection. By calculation, we get the resolution need to be 1231 LP per mm. This is a performance evaluation result on the new F-mount lens recently released by Basler. This comparison test is conducted in response to requests from customers who use other F-mount lens and demand for better performance. According to this result, it can be seen that Basler new F-mount lens offers significant better contrast at the same magnification and with the same size dot pattern. In conclusion, with the better performance of the lens, even lens with the same magnification can detect defect of the same size in more detail or detect smaller defect. Basler as solution provider, we offer wide range of lens to match with our camera. Now, I would like to give you an overview of Basler machine vision lens portfolio. Basler offers fixed focal length and telecentric lens. For fixed focal length, we provide C-mount, F-mount, and S-mount. Our fixed focal length well cover camera resolution from 2 megapixel to 45 megapixel. Image circle 1/2.5 inch to super 35 mm size. We provide a practical product approach to meet your need and with the superior optical performance. For Basler, the most important thing is to find and design the best solution that suit your application through need and delivery factory grade quality and reliability. Even if you don't have a choice in Basler optical portfolio, we are also capable of customizing them for your unique application requirement. From the table, you can see the distribution of our lens portfolio. We categorize fixed focal length into standard and premium product line. Both product lines support popular sensor format available in Basler camera, up to super 35 mm sensor format, as well as all common focal lengths. We launched telecentric lens with 1.1 inch, half inch, and 2/3 sensor size lens on our product roadmap this year. We also offer high-res S-mount lens from partner product. In the previous page, you may also notice we offer standard and premium lens for the same or similar image circle. Because of industrial usage, best technical fit is not always the best solution. Customers are always looking for the sweet spot to balance performance, cost, and development time. What is sufficient for their vision task, and what is the best solution they can get within their budget. The standard product line offers the excellent price over performance ratio and a strong basic performance for many cost-sensitive applications. The premium product line are designed and tested for more demanding applications, thanks for the high resolving power, low distortion, and low vignetting of the premium lens. They offer the best image quality. In general, standard lens used with camera with bigger pixel size, and premium lens match with smaller pixel size camera. Our goal is tackle all challenges our customer might face when it comes to finding the right optic for their vision system. Wherever you find it's hard to select, or with a complex specification, or too many criteria to consider, or the lead time issue, we have the solution for you. Last will be the key takeaway for today's webinar. First, basic lens selection for simple vision tasks can usually done by using free online tool, Lens Selector by Basler. This approach takes lens as a final component to be selected for the whole vision system. Second, advanced lens selection for demanding vision tasks need a holistic approach, taking both lens and camera selection into consideration. Third, it is possible to use magnification to determine which lens is needed, but you may not get the desired resolution by simply increase the magnification. Fourth, anti-aircraft provide a useful measure for you to compare and choose the best lens for certain application. But always keep in mind your specific application parameter when using anti-aircraft, as they are not set in stone. With these 4 points in mind, I would like to end the webinar today. Please remember, Basler is your reliable partner for lens selection. Feel free to contact us anytime. You may write to us via email here. Thank you for your time. Goodbye, everyone.